point out to you, and there's a bit of an analog here to what the Extension 2 students have been doing in conics, is that the way you make a question interesting or tricky is that you take it as a topic and then you see, well, in what ways can I connect this to another topic, okay? Now, in my experience, people look at this and they just freak out because they've never seen something like this before. But that's the whole point of mathematics. That's the superpower of mathematics. It's seeing through the exterior, which may look different, through to the core of what something actually is, through to its essence. So you see they're actually very, very similar. They're bound by the same principles, okay? So have a look at the situation with me. I'm going to take a seat in a second actually because I'm going to draw on this. You've got this big triangle here, right? And it's been subdivided in this following unusual way. They're taking, well, that's, I guess you could call it normal, right? They're taking this perpendicular, and then this perpendicular, and this perpendicular, and then they're using that, I mean, to look at a whole series of lengths. You're going to see this series come out in a minute, right? Then they want us to understand it, okay? So, luckily for you, what they do to begin with is they hold your hand and they say, look, just don't get overwhelmed by the infiniteness of the question. Just start small. Find the length of the interval BD in here, right? That's all you need to do, and hence show that the length of, and then they give you some other distances they want you to find, okay? So, have a go with me. You don't have the diagram yet, and we need some diagrams here. Let's start by just drawing this triangle in which theta inhabits, because that's the triangle that BD is in, right? So a simple diagram. We are looking for this length over here on the left-hand side. This is the one we're after. Okay. So putting a mental tag there for us. How do we find this interval? Well, you can see by the question, it's going to have something to do with sine and theta. You don't know what theta is, so therefore you just got to kind of leave that in the question, right? What is it that connects theta at this side and this side?
Sine theta.
It's just regular sine theta, right? Because you're in a right-angled triangle. So I'm going to say sine theta equals opposite on hypotenuse. So that's BD on 6. How many times, right? So the first part of this question is just what is BD? So I have an answer. Okay, that's good. That was the easy part. But then what they want us to do is to use that result, hence, use that result and get to the length of this side here. So this is a couple of triangles away, right? Now to try and make it a little clearer what's going on, this theta that we found in this triangle, there is a theta in every triangle that's on the diagram, but it's not entirely 100% obvious until you get down to brass tacks and try and work out what's happening, right? So, yeah, I'm on, good, okay. Have a look at that triangle there, right? In fact, I'll zoom in a little bit. So this is this ABD triangle that I'm talking about here. This is the one that we drew just a second ago, right? So there it is. Now you can see we actually know some stuff about the other angles there, namely that over here you've got that 90 degrees, that's no big deal. Since we're calling this theta, that means that the last remaining angle, ABD, is, well, what's its size? Yeah, it's 90 take away, it's the complement, do you agree? So I'm going to put this guy in here as 90 take away theta. However, we also know that AB, like this big angle in here, ABC, that whole angle is 90. Do you see that? So if you've got the complement of 90 nestled in here, and that whole angle ABC equals 90 degrees, then what must the other side be? Yeah, I've got theta in here, right? Do you see that? So therefore, I've got theta all over again, and I already know that this length in here, BD, let's use this. This length in here, we just said that that was 6 sine theta, right? So now, think about in this triangle, right? So all of this has to do with in triangle ABD. I really should have written that first. So now I'm going to look at the next triangle over. This is BDE. Do you see it? Right? This is one of the reasons why it's important to state which triangle you're in, because I'm going to have 3 of them all flying around, right? So in BDE, I invoke the same kind of thing, right? I'm going to say sine theta again, but it's a different pair of sides, right? What are the sides? What are their names? There's the opposite, right? Opposite on hypotenuse, because there's the angle opposite the right angle. right? So I'm going to say that is, what did we just say? DE on 6 sine theta, right? So now I know what DE is. It's just going to be 6 sine squared. So this is good. This is promising, because when you have a look back at what the question was asking us, you can see it's like, look, I need to just go one more step. I need to go one more step. But this is show. I can't just say, oh, cool, it looks like that. I need to demonstrate, how do I get there? What am I going to do? I've got to go through this same process, right? So I'm going to do the same thing up here, knowing that I have got theta here. Where is the complement of theta in this triangle? Yeah. Wait. Where is it? BDE. It's right up there in the top. So I'm going to put that in blue. So this guy here, that thin one, that is 90 take away theta. I should say 90 degrees, but you get the idea. Okay. Now, being that I've got 90 take away theta, but again, I've got that same right angle here that I mentioned before, right? So that means that this entire angle here should also be 90 degrees. Yeah, do you see it? So therefore, let's get rid of those guys. That means I can say that this guy is theta in here. Are you right? Are you following? So now I can do it one last time, and I can say in triangle, what? What triangle am I in? EDF. Okay, EDF. EDF. Again, I'm going to say sine theta. And again, it's going to be opposite on hypotenuse, but it's a different opposite and a different hypotenuse. The opposite is EF. And the hypotenuse is, yeah, DE, which we just established was 6 sine squared theta. So now, this is the result they were asking for. So I ended off like so. Are you happy with that? So this is just some simple geometry, okay? It's like, hey, right angled triangles, I did this back in year 9, so this is not complicated.